Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Karan Fernandes. He received his PhD in 2019 from the University of Calcutta, and since 2022 is a postdoctoral researcher at National Taiwan Normal University. Thank you, Karan, for agreeing to give this talk. The stage is yours.
Okay, thank you so much. So it's a pleasure to be here. And today I'll be talking about some work that I've done basically since I've been at NTNU. So it's on gravitational wave observables and double soft factors from the generalized Wilson line. So this is work with Professor Fong-Lee Lin in 2024, and more recently with Fong-Lee Lin and Chris White from 2026. So I'll go over this in four steps. I'll first discuss the broad overview of gravitational wave physics, which probably is not needed for this audience, but I'll still go ahead with it. So Einstein's equations give the statement that gravity is the curvature of space-time. And so if you have sufficiently massive or energetic objects which either merge or interact with one another, they cause significant and detectable ripples in space-time, and those are gravitational waves. And essentially, by orders of magnitudes, one can identify the amplitudes are proportional to the masses, what we call strain, and the frequency is just roughly proportional to the distance of separation. So dominant sources essentially involve binary black holes and neutron star systems. And apart from being a beautiful test of GR, they provide information on black holes and neutron stars. So it's people say it's ushered in the era of gravitational wave astronomy, and that's basically what we get from this. But we can also determine other things such as background space-time effects. That's an astrophysical media in which they propagate. Um, So the detections so far have been a little over a decade, and maybe it's a little over a decade. So it's through LIGO, the laser interference. Okay, you guys know what LIGO is. So it's a collaboration which has thus far made about 300 detections of binary systems with black holes and neutron stars. And this is a ground-based detector, so it measures strains in the range of 10 to the power minus 20 to 22. So this essentially corresponds to events involving tens to hundreds of solar mass black holes. And currently we're in the O4 run with LIGO, Hanford and Livingston detectors, the Virgo detector and the Cabra detector. Um, so in over the long term, I hope this is not covering it, but in any case, over the long term, we have space-based detectors, which will also be there. We currently also have a range of pulsar timing arrays. And schematically, this is what they describe. So if you measure timescales, these give you the timescales and the frequencies that we're talking about with each of these detectors. And these are the kinds of systems that you see as you go along. So at the moment, we can see things like uh, merging stellar mass black holes, but over the long term, we can talk about supermassive black holes and extreme mass ratio in spirals and the like. Um, so for the most part, this is what my work seeks to be interested in. So far, we have things like equal mass systems where you have like two binary objects which are merging into one another, and as they come closer and closer, the signals increase. This merger signal will increase until it reaches the in spiral. Until it reaches the in spiral signal will increase until it reaches the merger, and then you have the ring down. Okay. Then in general, we have unbound systems. And in these unbound systems, also you have a gravitational wave. As they get closer to one another, you have this large amplitude. And then this thing happens where the signal doesn't come back down. It actually has, I've written this in a more exaggerated way, but this would be the memory effect that we talk about, that the space-time remembers the scattering event that took place. And lastly, we have things like extreme mass ratio in spirals where uh, you have to concern yourself with both amplitude and frequency modulations. And both of these systems are topics of importance, and we need to derive them a little more carefully. So I'll explain that now. So the waveforms from numerical relativity depend on the quality of the endpoints. So if you have typically what happens is you start with good initial data and you have well-defined quasi-normal modes and coming down from the ring down of a merged black hole. And so the numerical relativity waveform can interpolate between these two. But when you have systems like extreme mass ratios or cases where you have a smaller black hole around a larger one, like the self-force problems, or even in systems where you have spin, these waveforms are not yet at the level that we would need for the space-based detections, which will happen in the future. And so there is a demand to derive theoretical results with increasing precision. And that is the domain of precision gravitational wave astronomy, where we use various techniques to derive higher and higher order, either post-Minkowski or post-Newtonian, or in the case of self-force corrected black holes. So these are the kinds of things that we are interested in deriving, these signals with these relevant corrections. Now, one of the things you may immediately think about is, okay, just use Einstein's equations and solve them. But this tried and true method fails after a few perturbative orders because you end up with these nested integrals which are ill-defined. And so just to give you a rough idea, the state-of-the-art result up to like recently was something which was derived in the 1980s, which was a 2 p.m. result. So there has been tremendous recent progress starting since 2019, where we got results for the 3 p.m. order, the complete 3 p.m. order, the complete 4 p.m. order, and now even 5 p.m. has been solved. And all of these results have followed from effective field theory approaches based on scattering amplitudes. So that has been one of the interesting developments over the past few years. So I'll give a rough description of the ideas involved in this. There are a wealth of talks on this by now, and much of it might be even standard and known, but I'll still describe the rough idea. So the in-spiral problem is what we're solving here. It's when the black holes are have not yet merged. And the results that you get for this are technically for the scattering problem, not for the bound problem. But there are ways in which you can translate the results for the scattering problem to the bound problem. There's a formalism known as boundary to bound. I won't go over that, but it can be done. So the main thing that goes into this problem are the scales that are involved. So in general, of course, you have a complicated two-body black hole system. They're inspiraling, they merge. But what ends up happening here is you have to describe your scales very carefully, and you have to describe your perturbation expansion carefully. So for the metric, we consider an expansion about flat space-time. So that's why it's called post-Minkowski. And for the black holes, you have to ensure that the distance of separation between the black holes are far larger than their individual Schwarzschild radius, okay, their radii rather. So when you do this, you end up with this as the relevant expansion parameter, that gm over c square b is far less than. And so you may still wonder, okay, why do we have like scattering amplitudes? And so I'll just argue it in a very schematic way. So suppose the two black holes are very widely separated and nothing happens. The two black holes just go from past to the future. But now if you move them closer and closer, you'll end up with corrections to Newton's laws. And so you end up with corrections to their straight line trajectories as well. And if you do even more, you'll end up with these additional kind of corrections, but you may also end up with energy losses, which are in the form of gravitational waves. And so what we are seeing here is essentially a system in which you may look at it as a scattering amplitude. Okay, so which tells you basically how a system of incoming particles evolves to the system of outgoing particles. And T here would be this interaction. So S is equal to 1 plus IT. If you did not have the T, it would just be the cases of two particles going from the past to the future. With this T, you account for interactions which take place. Okay. And so you can even have outgoing radiation in the final state, and this is all perfectly fine. The only issue, of course, is that all of this is quantum, and we're talking about classical black holes and classical radiation. So how do we get this? And so we have to extract classical physics from essentially a quantum object. So this is where effective field theory comes in, and these scales become very important. So the first, there are basically two main assumptions that are involved in this, in the post-Minkowski case. The first is that, as we mentioned, the distance of separation is large between the two black holes. So it's really in the early in-spiral phase that we start talking about that this is being that we're starting from a very widely separated black holes to begin with, and it's in the early in-spiral stage. So at that point, you have large angular momenta because the individual black holes, you basically have B, which is large, and P is at least order one. So J is far greater than one. And then what ends up happening when you have large angular momentum is, by the correspondence principle, you can show that you end up with a nearly continuous spectrum given large eigenvalues. And so that's basically how you bypass discrete expectation values and can essentially talk about a continuous spectrum. But of course, with amplitudes, you also have to worry about particle production effects, right? You can have loop effects and particle production effects when we're scattering particles. So this you suppress by ensuring that the Schwarzschild radius is far larger than the individual Compton wavelengths of the black holes. So that would be equivalent to also stating this in terms of the de Broglie wavelength. Okay, and so ultimately what you end up with is this hierarchy of length scales, that the impact parameter of the two black holes are far larger than the Schwarzschild radii, which themselves are far larger than Planck's constant divided by P. And so when you do this, you can essentially take a given scattering amplitude and compute its results. You enforce these scales and you can derive classical results from them. Okay, so this is like a very very quick review of like the field as a whole, but this is essentially what goes into it. Okay, you also need, there are a lot of techniques for computing the scattering amplitudes, but I neither can nor will go into any of those details here. Instead, what I will do is talk about one facet of this, which is radiation. So for radiation, you can compute them from scattering amplitude techniques in one of two ways. The first is you compute your amplitudes and you have these things called unitary cuts, and you have to compute these cut amplitudes and calculate and check them and compute them in detail. But there is another way you can do this, which is you have coherent states. So the radiation that is being emitted from this binary system that's interacting, you can describe them using coherent states, and they indeed yield classical expectation values. So to basically describe this, and this is just a review of stuff for coherent states. If you have the operator that creates a graviton and it acts in a coherent state, described by this alpha, then this alpha, you get the eigenvalue of alpha and alpha. Okay. But this requires that the state alpha is given by some exponential operator acting on the vacuum, on what you'll call the true vacuum. And this delta here, this exponent of this exponential operator, is given by some alpha star A minus alpha A dagger. So this is some unitary operator. We call this alpha the wave shape, and A and A dagger are just in this case, the annihilation and creation operators of gravitons. So one of the features of this state is, if I were to compute the expectation value of h mu nu with the true vacuum, I'd get nothing at all. But if I compute the expectation value with respect to these coherent states, I pick up the I'll pick up the eigenvalue. I'll pick up this alpha over here, okay, which I should have noted, but never mind. So this expectation value of h, which is which will be like alpha into epsilon mu nu. That is this W mu nu. And this is nothing but the waveform. So one of the features of this approach is that it can quite simply give you classical expectation values that you're interested in from the binary system that you're talking about. So of course, then the only question to ask is how does one determine this alpha? Because if you determine this alpha, you've actually determined the waveform, among other kinds of radiative observables you can talk about. So to describe what is this alpha, and one of the ways you can do this, I'll take a small detour and talk about soft factorization of scattering amplitudes. Okay, and I'll discuss it in the context of this binary black hole scattering problem. So let's call the incoming state P1, P2. So those are the two black holes coming in, and we'll just denote that by P. And for the outgoing states, we'll call them P3, P4. They have momenta P3, P4. We'll call that P prime with no radiation. In this case, this T, the interaction that we had, would determine some A4. It's some 4-particle process. Two black holes come in, two black holes go out. Okay. But now suppose we had a bunch of gravitons coming out, n of them. Then my outgoing state would be P prime with K1 to Kn. Okay, and in this case, I'll end up, instead of a 4-point amplitude, I'll have a 4 plus n-point amplitude. Okay, so now what is the soft factorization? It's when these n gravitons, which I have here, are taken in the limit where the momenta are going to zero. So the 4 momenta, if you take them, if you take the energies of these gravitons to be zero, more specifically, then this A4 plus n object over here picks up some overall factor, which we call a soft factor, Sn, and times this A4. There are, of course, additional corrections and other things to talk about, but very schematically, this is what is going on. And when I say K1 to Kn going to zero, in this case, I'll at least mean the simultaneous soft limit. There are other things you talk about, like consecutive soft, where you first take K1 0, then you take K2 0. But I'm not distinguishing those cases for now. There are different soft factors for the different ways in which you take the limit. Okay. But what is true is there are universal contributions that you can pick up, meaning regardless of the type of amplitude you're talking about, you can pick up pieces which hold for all scattering processes. So these are known in the case of single soft factors and double soft factors for gravitons. And so I will be particularly interested in that. Okay. So single soft meaning we have only one graviton and we take it to be soft. Double soft would come when you have two gravitons and you take them to be soft. And this is what is known up to now. I didn't want to write the explicit form of the expressions to bog you down, but I'm just going to denote them. So the single soft factor is known up to something known as the subleading order universally. So we have like this leading order term, which I'll call F0. This was derived by Weinberg in the 1960s. Then we have like F1 and F2. This would be the subleading and the sub-subleading factor. And then we have additional pieces. Okay, but these are like very well-known pieces which we have. And then, of course, there's a double soft factor, which is a part of the double soft factor comes from products of single soft factors. That would be this top line here. So the product of two single soft, so single and subleading single will give you some pieces. But then we have these additional pieces, which I'll just call A0 and B0 for now. Okay. And this whole thing here is what I'll call the double soft factor, which was known prior to our work. Okay. So these expansions describe the universal terms which are currently known. And okay, so this is up to sub-subleading order in the single case and up to leading in quotes for the double soft case. Okay, so now given all of this, I can describe what we know about how these soft factors enter into a description of gravitational waves. So let's just focus on the single soft case, because this is actually what has been used prior to our work. So in the single soft case, this leading Weinberg factor, okay, this F0, was shown to provide the leading 3 p.m. results, radiative results from binary scattering processes in post-Minkowski scattering. So if you just, in place of alpha, if you have this F0, okay, so it's literally like this, you can get the late time waveform, the late time radiated momentum, and late time radiated angular momentum at 3 p.m. order. So that was a bit interesting. And so the corresponding waveform, as I just said, we'll denote by, let's say, W mu nu G. And this recovers the linear memory effect. Okay, so that's the leading late time or low frequency result you get for the waveform. You can, of course, also talk about the full waveform. That also has been computed at 3 p.m. order. Okay. And but the analytic expression for it was not properly known till about so the full waveform was derived 2 years ago, well, 3 years ago, and the analytic form of it, comparing it to that, was 2 years ago. Okay. And what they found is what is known essentially is that if you consider the expansion of the full result, the soft expansion, it matches the soft expansion of the waveform, the full waveform matches the soft expansion that I was just showing. Okay, that you have a leading soft, then subleading soft, then subleading soft. So essentially, then the soft expansion has some utility. And the question then is, how do we generalize this result to higher orders in G? Because that's not immediately clear. Because if you see this, all of these terms over here are at the same order of kappa, right? And so kappa into the waveform, kappa into whatever you get will all be G. And if you had to get something at 4 p.m., you'd need something which is G square. So then, of course, you can ask, well, where does that really come in and how do you compute it? And of course, generalizations of coherent states, if any, are also a big question. Do they exist and how are they important? So that is basically what motivated our work. So on the one hand, we wanted to explore this using Wilson lines. And that is one way in which you can factorize amplitudes in which graviton emissions exponentiate. So you can get higher order, you can talk about higher order corrections and generalizations. So in this expression, this h mu nu refers to soft gravitons. They can be both on shell and off shell. By on shell, I mean that k square is 0 and off shell is k square is not 0. This SEH eta plus h is the Einstein-Hilbert action in the phase, which is expanded about flat spacetime. And this F is what is the gravitational Wilson line until 2022, well, till 2024, and till recently, this was the expression which is known, which is it's given by exponential of F0 plus some A0. Recall F0 was this thing I denoted in the single soft graviton case, and A0 is one of the terms in the double soft case. Okay, so this was known, and what we were interested in is what is the corresponding dressing operator given this this dressing? How do we derive it? So that we can talk about generalizations of coherent states. And two, what are the kinds of radiative observables you'll get from them? So I'll just summarize the formalism a bit, and then I'll talk about what we did exactly. So what we're basically doing is we have, let's say, a scalar field, scalar because we're not dealing with like spinning black holes. So we have a massive scalar field and a background gravitational field. And from this, we can identify the form of the action, which is given by like phi star into some object phi. Okay, and this H, because we've expanded about flat spacetime, there is an infinite series expansion that we can talk about. Here, I've expanded it up to second order in kappa. And now what you can do is consider the inverse of this operator. Here we are calling it an operator because we have promoted all these derivatives to p's, and we've used a prescription of, we've while ordered it, if that is known, fine. We're talking about so we've used an ordering of the p's and the x's, and then we can talk about the inverse of this h. So this basically follows from using this kind of formula where you have 1 over h is given by this, and where we use this description of plane waves in terms of x's and p's. And so we introduce a set of states, and we use these kinds of we use this kind of resolution of the identity. And what you can end up with is an expression for h inverse evaluated from an initial position to a final momentum as an integral of a whirl-line time, path integral over p's and x's, okay? And in terms of this object over here, okay? Now, because we have interactions, namely that h kappa and h kappa squared and so on, we can't solve it exactly. So we have to solve it about a known solution. So the appropriate thing to solve is about flat spacetime, and in the absence of any interactions. So accordingly, we can use these solutions we can solve about iconal trajectories. Right? So we can solve given x in terms of xi plus pt plus some fluctuations. Solving for these fluctuations is what's important. And p in terms of some final momentum plus pt. Okay. And when we solve it about these iconal trajectories, because they're being solved by about the late time solution, we pick up all these corrections from the gravitons as soft graviton corrections. Okay, so that's that's a feature of this program. And so here I've just given some more steps. So we can write this propagator. Eventually, it takes on this form times some ft, and we solve it first with xi equal to 0. Okay, so this xi we just set to 0. If we don't set it to 0, which will come later on, we pick up orbital angular momentum terms. Okay, so because with any x's, you also end up with px pieces, which are the angular momentum pieces that we'll get. And this is important for subleading soft graviton terms. And we'll discuss this later on. Now, okay, so we compute all of this. The only thing is that this gives you the propagator, meaning the propagator for the for the particle that we're talking about in the background field. So it's got the background field contribution and the particles contribution. We just want the background fields dressing contribution. We don't want to talk about the particles themselves. So accordingly, we amputate the last step, if you will, is we amputate the contribution from the free propagator. So this would be the propagator of just the external legs and the amplitude. This is for only one of them, by the way. So we pick up, we will multiply by this propagator for the hard particle, this PF. And then whatever is left when we take the asymptotic limit is the soft dressing contribution. Okay. So this F is for only one of the particles. If we do them for all four, we will end up with the total dressing for the whole process, for the whole 2-to-2 process. And now what we were interested in is performing this entire process, this calculation, but now instead of H as some classical fluctuation, some classical perturbation of the background, we replace them with H hat, which are the radiative modes that we care about. This would give us this would convert the Wilson line we're talking about into an appropriate generalization of the coherent states, which is what we're after. Okay. And so H kappa gives you the coherent state part. H kappa squared will give you the double soft contribution. And one of the things we noticed as we were computing, as we were calculating this, and as it was going on, is that the dressing is not manifestly gauge invariant unless the two gravitons are collinear. This was a surprise for us at first, and we did not notice this. So the Weinberg factor, this F0, right? The F0 which you have in the gravitational, in the single graviton case, that is invariant under h mu nu going to k mu xi mu plus k nu xi mu. So that's what I mean by gauge invariant. But this was not the case for the double soft piece, unless we also took the k to be collinear with L. So we did take this, and later on we will resolve this. But this is the thing that we assumed in the 2024 paper. So we have this condition essentially. And then when we take this, we assume this condition and we proceed, we end up with some, this is just the summary of the result, that we have this F giving you some kind of a dressing operator, hence the hat. There's like a hat with a kappa and a hat with a kappa squared. So the hat with a kappa is basically what was talked about by Veneziano et al. In talking about 3 p.m. observables. The hat with the kappa square, on the other hand, is this double graviton generalization. It has A dagger, A dagger, A dagger, A dagger, A, but with the other L and K flipped. And this is the collinear condition that I was just talking about. Okay. And now what you can do is you can use the BCH, the Baker-Campbell-Hausdorff formula, and given some exponential of a sum of two operators, you can write them as a product of two exponential operators. And one of those operators ends up with a tower of corrections. So that would be this coherent state operator in this case. You end up with not just the delta naught kappa, but also like kappa cubed corrections, kappa to the fifth correction, and so on and so forth. We've only we truncated it at kappa cubed. I mean, you can in principle go to higher orders. And so this operator as a whole is actually nothing more than a squeeze coherent state. So we have what we were kind of looking for, that if you simply take a gravitational Wilson line, and this is a factorized form of the amplitude, and you just follow it by your nose with radiative modes, you end up with, in general, generalized coherent states. But if you stop at if you stop at quadratic order in the gravitons, you end up with squeeze coherent states. Now, this delta kappa squared here, this second operator that we're talking about, this is a squeezing operator and doesn't yield classical expectation values. It may be very interesting for quantum effects, which are in fact being explored, I believe, right now in various settings. But at the time that we wrote this paper, we were only interested in the classical observables. And this object here is this modified coherent dressing operator. The kappa part is what was talked by Veneziano et al. But this kappa cube now ends up with a product of the double soft piece and the single soft piece, as we can see here. Like it has A0 with F0, A0, F0, and so on. Okay. And so if you now compute an expectation value, you get the piece, you get the contribution from this kappa, which would be nothing but those late time 3 p.m. results that I spoke about in the review part. But you'll also end up with this kappa cubed contribution. And in principle, if you wrote fifth and so on, you'll end up with those corrections as well. So this kappa cube provides a partial correction to the 3 p.m. results, and these are at 4 p.m. and higher. Okay. So we can get, and we did derive the results for the waveform, the emitted momentum, and the angular momentum, meaning even the total angular momentum, meaning orbital and spin. I'll only comment on the waveform result. So for the waveform, as I mentioned previously, what Veneziano et al. Showed in their calculations is that this WG gives you the linear memory effect. This is the late time change of a space-time after a scattering process. But this WG square, what we were able to show is that it actually is identical to the nonlinear memory effect, also known as the Christodoulou memory effect, provided you sourced it by an emission of nearly soft gravitons. So let me clarify what I mean by this. We compute this and we get an answer. Okay, so that's WG square. On the other hand, I just take the Christodoulou effect, and I replace the T mu nu term in there with the stress tensor of nearly soft gravitons. It can't be soft, otherwise it's zero. But you put a cutoff and you calculate what you get, and then you compare this result with this. So this result has contributions where it picks up terms from more than one leg. So the exchanges are in a funny way, but there's also the leading contribution which comes only from one leg, which would be this, what we call the ultra relativistic limit for the hard particles. Okay. So in that limit, this result which you get over here matches exactly the Christodoulou effect. It's a bit surprising at first to us, but I guess it sort of makes sense. And the reason why this is interesting is more recently, as in last year, uh, these authors, they argued based on a scattering amplitude calculation that most likely you need some generalized coherent states to derive the nonlinear memory effect. In particular, they argued for generalizations of 5-point amplitudes. 5-point amplitudes would be the ones which, when you cut, you can get the waveform. But like here, they've argued for generalizations of that in order to recover the nonlinear memory effect. So perhaps the ideas and methods that we had in this paper could somehow flesh this proposal a little more. Okay, so that was our 2024 result. But there are, of course, two glaring issues. The first is all of our results are only true in some kind of collinear limit. And we would like to, of course, talk about it more generally. But there was another issue that we noticed, which is a little more serious, which is it's inconsistent with the known double soft factor. So what I mean by this is the Wilson line that we derived has soft contributions, multiple soft contributions, right? So if you took it to kappa, you'll get single soft, kappa squared, double soft, and so on. So of course, when I expand that exponent, I had better recover the single soft factor, the double soft factor, and so on. But what we find is when you expand that f function that we had, this fph, you'll have like the 4-point amplitude, you'll end up with f0, and then you'll end up with something like this. Now, this top line seems okay. Like you have the case with no gravitons, then you have at least the leading term, the leading single soft factor. So this also is okay. But this is just wrong. This is not the double soft factor. You're missing the single soft and single subleading soft, and you're missing this term called B0, okay, which was also there. So what happened and why did we not get these terms? The reason is that while you can get away at single soft order by ignoring subleading contributions, it's just some artifact, some extra piece that we don't care about. At double soft order, you have to care about these terms that are not immediately attached to external hard particles. So I'll explain that through the schematic slide. So imagine you have a 2 to 2 amplitude like this, right? Two particles coming in, two particles going on. This F0 and this A0, which is right here, you can see that the graviton is basically the vertex is those which are attached to the external particles. So single one is like this, double one, you can have like a double graviton vertex, or you can have two different ones. Okay, so this is what is there. And products of them are also fine. So you have F0, F0. The problem is in this column over here. When you have subleading contributions, there are exchanges between the hard and the external, which I've schematically drawn this way, but it's actually it should be between the external particle and the hard. Okay, so those kinds of things are missed, and this B0 involves two gravitons emitted from an off-shell from an off-shell graviton. So there's basically an off-shell graviton, and then you have two gravitons coming out. So you can see like this is a triple vertex, actually, and only two of them are on-shell. So that is why it was missed. We have to account for these kinds of angular momentum pieces and off-shell graviton pieces in order to get the answer. So I'll start with the latter, the graviton pole piece. So in order to get that, we actually need to go back to I hope that this is sort of like that. This was the original factorized Wilson line form that we were talking about. The only thing that was missed is we have to actually perform this integral over here carefully over the off-shell gravitons. So contained in S Einstein-Hilbert action over here is the triple graviton vertex that we want. And by good fortune, it is already exponentiated, and you can perform this Gaussian integral. Okay, so when you perform it, you end up with this f, which was here originally, going to some f bar, what I'll call f bar. And this f bar now picks up this b that we were after on the nose. Okay, so everything is looking good so far. The interesting thing, of course, is that not that triple vertices give you this, but that here it comes in an exponentiated form. So that was like, for some reason, it wasn't, to our knowledge, it was not mentioned. So this triple graviton piece also exponentiates. Okay. And then we have subleading pieces. So now for the subleading pieces, we have to use this thing called Low's theorem. Oh boy. We have to use this thing called Low's theorem. Okay. So we have to talk about X contribution, Xi contribution, like some initial separations which are in there. So we introduce an X dependence in the dressing, meaning the Wilson line itself, and we have an X and H dependence in the amplitude. Okay, so now we have to, So now what we have to do is solve it for non-trivial Xi's. And the X dependence in this F is coming through phase terms like e to the power ikx and lx for single graviton kind of pieces, and e to the power I k plus lx. So terms like these phases are what's here. And for A4X, we use an ansatz. So you can start with something with no graviton, something with two gravitons, with one graviton, with two gravitons, and so on. And they have coefficients of undetermined functions, which we have to solve for. And so now what we want is this result to be gauge invariant. So we impose gauge invariance by performing this transformation on H's. We have two gravitons, one with, let's say, momentum K, one with momentum L. We'll end up with things like this. And so we just have to contract with the K graviton and the L graviton and solve the identities that we get. And this way we can solve for A4X completely in terms of A4 and some other kind of expression. And so when we do that, that's a very long calculation, but when you do that, you'll find that this F bar goes to F tilde. Okay, after doing all of this. In principle, this is not exponentiated, but since we are dealing up to double graviton order, we can write it in an exponentiated form, and we have argued why it likely exponentiates. If it did not, you would not recover the same. I mean, if this F1 and F2 did not exponentiate, you would not get the answer that we do in its Low theorem form. So anyway, so this is the dressing that we need, this F tilde. It's literally the single soft factor up to subleading order. Plus we have like A0, B0, which we have. And an upshot is we got new terms which were not known in the literature. This A1 and B1, I've denoted them as that. And this would be a subleading double soft factor term, which is completely new in the literature as far as we can tell. And so just to give you an overview of the result, this graviton dressing had the stuff that Veneziano and all talked about, had like this Weinberg piece, this F0, but not F1 and F2. And then originally, the double soft graviton calculations which were there talked about like Born, those things with like two individual double gravitons on external particles and this double graviton on an external particle. But what we were able to do is derive this graviton pole contribution. And by dot, 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 I mean all subleading terms, that single and double soft order. So the graviton pole term exponentiates and follows from the Einstein-Hilbert action in the path integral phase. Lowe's theorem provides these terms. And collectively now this dressing exponent and this dressing recovers the double soft factor up to first subleading order. And it's completely gauge invariant. And in our paper, we also discuss the dressing operator. We didn't go over the entire calculation as we did in the 2024 paper, but we argued what the form of the operator should be. It's again squeeze coherent states, but we haven't yet addressed the observables, which we will probably do in forthcoming work at some point. But that would provide a more general nonlinear memory effect calculation beyond the collinear limit. So to summarize this talk, I hope I'm doing okay in time. Okay, good. Yeah. So to summarize this talk, the factorized form of scattering amplitudes using Wilson lines, we've seen that it provides a squeeze coherent state description for, well, technically for low frequency gravitational radiation up to double soft order. The coherent state corrections follow from contractions of single and double soft factor terms. And so one of the consequences of this is it's non-linear in nature. They provide non-linear radiative observables. And one place where I explicitly discuss this is the non-linear memory effect. In a limiting case, of course, where the source of the non-linear memory effect is nearly soft, the stress tensor of nearly soft gravitons. Now, our results might support this recent proposal in this paper on the need for generalized coherent states in describing the nonlinear memory effect, but we haven't yet verified it one way or the other. And our most recent paper provides a more general double soft graviton dressing beyond the collinear limit. What is sort of appealing in this is that we have bridged the discrepancy which was there previously between Wilson lines and double soft factors. So now we have a result which is consistent with the known double soft graviton theorem, but we also have derived a new subleading double soft factor result which was not known in the literature. So with that, I thank you for your attention and be happy to answer any questions you might have. Thank you.
Thank you, Karan. Are there any questions from the audience?
I hope I wasn't too fast or.
You were perfect in time.
Okay. No, I mean by the substance. Okay. I'll wait. Yeah, I'll be happy to answer any kind of question. I might have gone a little too fast and I'm a little tired because it's a bit late, but I will make up for it by answering as best I can.
Can you maybe tell something about the applications of the methods? I mean, I'm not familiar with the topic.
By application, you mean like, what do you mean exactly?
Like which effects we may calculate from that, or how it benefits some calculations.
Okay, so the calculation in question is okay, so I can maybe mention one of the driving forces for this. So this is all post-Minkowski. And there is a need to derive high order post-Minkowski results. In general, radiative observables are harder to derive. Okay. What we are leveraging in this calculation is the universality of soft factors and their presence in Wilson lines. That is one thing. So we get some answers the answers are whatever they are, they're late time observables, they're the dominant contributions. The trade-off is not the full answer. When people talk about precision gravitational wave observables, you want to derive like a full 3 p.m. waveform or a full 4 p.m. waveform. So here what we do is we're getting leading order pieces, but we're not getting the full answer. In any case, it gives you an a window into analytically understanding these processes in the binary system. That's one of the driving motivations of this. The second is that this approach, in principle, can be generalized to spinning systems and curve systems. Even though I've computed this for like we've computed this essentially for iconal trajectories about flat spacetimes, you can easily consider, well, not easily, but you may consider any curve spacetime solutions about curve spacetimes, or you can consider spinning external systems, or you can consider things moving in a background, in a more complicated background. You can consider things moving in a background with plasma. And so all of these things may give you additional effects that are otherwise not so straightforward to compute using the conventional scattering amplitude techniques. Now, after you're done computing all of this, of course, comes the question of can you show that what you've computed fits into the known EFT formalism? There are many things being developed right now to bridge computations with world line formalism, the KMOC formalism, and so on. There are a bunch of different formalisms in which you can derive these things. But I would say like one of the features of this is it's you get neat universal answers, but they're not necessarily maybe the most flashy or useful answers for a because the numerical relativity guys, they give me a full 3 p.m. result. So it is what it is. It has its trade-offs, like with every system that is there in this field.
Thanks.
I hope
And
I answered.
You gave me an idea.
Okay.
Okay. Shivan posted a question in the chat. Question one, the structure of soft graviton factors for waveform seems to be similar to the EFT calculation of love numbers and the associated phase correction. Are these two formalisms related?
So for the soft factors are completely coming because of radiation that you are factoring out. Okay. The love numbers is coming from a higher curvature kind of terms that you're computing. So the all of those things would come as coefficients of higher curvature pieces. So the expansions are different. They're not of the same character. Could they be related? Sure. If the higher curvature pieces have like some radiative contribution in them, right, then they contribute also to, let's say, some non-universal pieces of soft factors, which I have not addressed here. I've only addressed the universal pieces. So in that sense, they may address a part of the answer, but I'm not entirely sure. They also come from what I understand, they come from a different way of approaching it. So soft factors come from starting with an amplitude with radiation and taking the limit of that radiation to zero, and you pick up like this factor. Okay. Whereas the love number pieces or things, anything related to tidal corrections and of the like, they come from formally from expanding higher curvature terms, starting from the action and then proceeding. And then you do like a matching calculation later on. As far as I understand, I could be mistaken in some way, and I would welcome any like pushback so that I may rethink it. But I think that those are two qualitatively different ways in which you proceed. But there might be a relationship between the two for sure. And what is the second question?
I think it's not there yet.
Okay.
The second question, because here's Q1. Uh,
So in any case, like those are finite size corrections, and a part of the finite size corrections may be related to non-universal soft terms. I'm not entirely sure if that would be the case, but that's interesting enough to consider. Yeah, there might be a relation between the two. But
Okay.
it would be not.
Now there's also question 2. Given that the soft graviton expansion should be applicable to all theories containing massless spin 2 gravitons, can we parameterize diagrams as generic case-based polynomials and potentially be more efficient than PPN expansion?
Let me maybe see the question.
Somewhere below should be a chat window. Or shall I just read it again?
Maybe just read it again.
Okay. Given that
I
the
see
soft
it. I see it. I see
okay.
it. I see it. I see it. Okay, good. Given the soft graviton expansion should be okay. Yes. So I don't think they work in quite the same. So when first of all, what do you? I'm not exactly sure what he means by the parameterized post-Newtonian expansion. So let me address this in two ways. So the first thing is there is an amplitudes way in which you compute post-Newtonian calculations. This is the approach by Luc Blanchet and others. That has a non-relativistic EFT nature to it. Okay. Now you can ask, is there a way in which that computation relates to PPN computations? I'm not exactly sure. There may be. Let's assume there is. If there is, then there should be a way in which we can talk about the soft expansion here, tying into the post-Newtonian effective field theory there. And then you could find some connection with the PPN expansion. But I don't think it's not of the just because there's an expansion. At least I don't see the connection between the two right now. The the one okay, so the way to even look at it maybe qualitatively is the soft expansion is an expansion from very late times building inwards. Okay, so think of the waveform or radiative observable. So it's massless spin to gravitons, as you mentioned. But you can also do this for light. You can do this for anything. You take this radiation not just at null infinity, but at the future of, so it's at scry plus plus. You're building it from very late times, and you're building inwards when you take the subleading effects. Whereas this parameterized post-Newtonian thing is corrections at when you're building up from small velocities. So I don't think they're qualitatively of the same kind. Uh, that said, if you compute with post-Newtonian effective field theory and you get a result which has a soft limit, and you want to compare how this soft expansion in that case compares with the soft expansion in the relativistic case, which is what I'm discussing, that might exist. And its connection with some PPN might exist, but I'm not sure. I hope that made sense. I'm explaining with hands, but I'm trying.
Maybe wait a few seconds. Thank you. Okay, are there other questions? It seems not.
Okay.
So then, thank you for the nice talk again, Karen.
Thank you
And
for having me.